So we're going to do, today can go pretty quick. I think the video is generally about 20 minutes, 18 minutes. And we start with Descartes' rule of signs. So we're going to pick up where we left off yesterday. We know now the rational roots theorem, and we're good at it, aren't we? Well, let's talk about some guesses, and let's talk about good guesses and bad guesses. X squared plus 5, or x to the third plus 5x squared plus 2x plus 8. What's a bad guess? A positive number. Very good. Descartes recognized that. Descartes, in some ways, kind of the father of our modern algebra system. So if you've ever heard about the Cartesian plane, which is the xy axis, Cartesian, Descartes, okay, so that's where that comes from. So the dude was a serious mathematician. He put some nice things together. He said the number of positive real roots of a polynomial is equal to the number of sign changes in P of x or less by a factor of 2. No. So what does that mean? I'm going to graph a cubic. A cubic could look like this. Could also look like this. And it could also look like this. So consider these three situations. The first graph I drew, how many solutions does that graph have? It has 3 real solutions. 1, 2, 3. How many real solutions does the second one have? 3. 1 and a double. How many real solutions does the last one have? 1. So if it only has 1 solution, it has a third-degree polynomial, then there must be 2 imaginary. So imaginary solutions come in pairs. We're going to show you that more on Tuesday. Imaginary solutions come in pairs. So that's why it will be less by a factor of 2. You can see in this either one of these situations we have 3, and this one we have 1. B. Rodden, what do you want? I'm not going to teach you on Monday. Monday we're going to do complex numbers. You want to switch the order of things? Yeah, we're going to do Tuesday. Monday we're going to cover complex numbers. It's going to be a really good time. And then on Tuesday I'll teach you the fundamental theorem of algebra. All right. Got it. So the number of negative real zeros, roots, or solutions of P of x is equal to the number of sign changes in P of negative x, or less by a factor of 2. So here's what we consider. Look at the first polynomial, 3x to the third minus 4x squared plus 5x minus 2. The number of positive real solutions will be the same as the number of sign changes or less by a factor of 2. Here's what sign changes mean. Is it 3 positive or negative? Does it switch? That's one switch. Now you go from negative to positive. That's a switch. And that's a switch. So it has 3 or less by a factor of 2, so or 1. We don't know for sure which one it is. Yo. Is 3 positive or negative? Is 4 positive or negative? So it switched sign. It switched from positive to negative. So that is one sign change. The number of sign changes that exist in P of x indicates the total number of possible solutions. I can't tell you why that is. We'd have to do the proof and we don't have time, but Descartes sure could do it for you. So now I'm going to consider P of negative x. As I look at P of negative x, I plug in negative x for x. I get 3 times negative x cubed minus 4 times negative x squared plus 5 times negative x minus dos, which is Spanish for 2. What is negative x to the third? Yeah, so if we multiply that, we end up with a negative 3x to the third. How about the next one? It will be a negative x squared will be a x squared, then the minus 4 will make it a minus 4x squared. Minus 5x. Very good. So we have negative real solutions will be equal to the number of sign changes or less by a factor of 2. There are 0 sign changes. Less by a factor of 2. I will try showing you one more time. Because that is what Descartes told us to do. So again, if you consider the graph of a cubic, this one has 3 solutions, correct? This one also has 3 solutions, right? So it looks like it will look like one of the first 2. But suppose that it had an imaginary solution. They come in pairs. So that way we would only have 1. Okay. How about this? Suppose you're doing the quadratic formula, and you come up with, say, negative 3 plus or minus the square root of 4 over 2. How many solutions does that represent? It represents 2 solutions. But if it was a negative 4, then it would have imaginary, right? And it's going to give you 2 results, isn't it? You can't come up with any situation where you end up with 1 imaginary, can you? There we go. All right. So last piece here before we move on to the next problem is this. The total number of real solutions will be the combination of the positive and the negative. So 3 plus 0 is 3. Or maybe it would be 1 plus 0 is 1. So the total number of real is going to be 3 or 1. Okay? Yes. If you subtracted 2, you get negative 2, and it is not possible to have a negative number of roots. Okay, let's try the next one. Question, Ella. Number of positive reals equal to the number of sign changes in P of x. How many sign changes? There are none. Four or 2 or 0. Yes. If it was the 6th power, it'd be 6 or 4 or 2 or 0. Because, what's that? No, not ever have, but I will say it went a lot slicker first and third hours, so it's okay. I get it. It's 6th hour. I got it. So, all right. So then P of negative x is negative x to the 4th minus negative x squared minus 1. Do I end up with a positive x to the 4th or a negative x to the 4th? A negative x to the 4th. Well, sure. Okay, that's all right. Negative x to the 4th would be positive x to the fourth, and then you attach the negative. Powers before multiplication. Question. Descartes says that we have to do p of negative x. Descartes says if you want to know the number of positive real solutions, we look at p of x. If we want to know the number of negative, we have to do p of negative x. Yes. Okay. Negative x squared is x squared. Attached to negative, it's a minus x squared. And I have a minus 1. So now we use that to identify the number of negative real. How many sign changes? There were 0. So the total number of real solutions is 0. So that means trying to find these solutions, we would be in vain, trying to find any real solutions. The fact is, if you graph this, it looks like that. It sits below the x-axis. It never crosses it. There are 4 imaginary solutions, okay? Here's one other piece I would like to draw your attention to so that you can save time on your assignment, okay? Negative 3x to the third, minus 4x squared, minus 5x, minus 2. If you notice, this was p of negative x, right? Look at what happens. If it's an odd power, it changes sign. But if it was an even power, it stayed the same sign. Odd power, changes sign. Even power, same sign. Same thing here, look. Even power, same sign. Even power, same sign. Because even powers will make the negatives cancel out, and you'll just end up with the same piece. So that will help you go quicker through some of the problems, and I'll show you later on. Okay. Now, anticipating how the last piece went, please focus a little bit more in depth on here. I'm worried how this will go, okay? So what we want to do now is we want to put forth another small piece that Descartes said. And what he said was, sometimes we end up with ridiculous number of choices. For example, yesterday our last term was 48, which meant that we had choices negative 48, negative 24, negative 16, negative 12, negative 8, negative 6, negative 4, negative 3, negative 2, negative 1, 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. Well, Descartes said, I don't really care for that. I would like to get rid of a lot of the choices. We already showed you that Descartes' rule of signs can help you understand if you get rid of some of the positives and some of the negatives. He also said there's another way we can identify if maybe there are no solutions that are greater than 2, or there are no solutions less than negative 6. So we can focus on kind of a middle ground. And he said there's an upper bound and there's a lower bound. And here's how you find it. When you do your synthetic division, if you use b, and b is a positive number, and you divide it into your coefficients, if the results come up positive, positive, 0, positive, 0, positive, positive, if they're non-negative, then b is an upper bound. And what that means is that there are no solutions that are bigger than b. I'll be honest, I don't use this that much. It does come up from time to time. If a is negative, then a might be a lower bound. It's a lower bound if positive, negative, positive, 0, positive, negative, positive. If it switches sign, and 0 counts as a sign change, then a is a lower bound. What we just learned about predicting positive real and negative real on the scale of importance for your test, on a scale of 1 to 10, that's a 10. You need to know positive and real solutions like the back of your hand. This is, about a 2 on the scale of importance, okay? I'm going to show you how easy this works out and the type of examples you're going to be able to do. It says, show that the polynomial p of x has real zeros that lie between -3 and 2. That would mean that 2 would be an upper bound, right? We're going to show that 2 would be an upper bound. So I'm going to divide it into 1, 0, -3, 2, and -5. Remind me how I do this. Braden, question. You're 100% right. And the fact is that this actually doesn't have any real solutions. I'm sorry, any rational solutions at all. I'm just going to pick an example that will show that to you. So you're absolutely right, Braden. This is not a good example of something that you would actually use in all practicality, but we'll show you that next. Okay. So as I drop this down, I get a 1. I get 2, 2, 4, 1, 2, 4, 8, 3. What do you notice about all your resulting coefficients? They're all, and actually the term is they're all non-negative. So meaning 0 can pop up. Okay? Thus, there are no solutions greater than 2. So what that tells me is, if this was the type of polynomial, which it's not, but I could just get rid of those choices. All right? What's that? Well, so for example, on your test, I would say this. I would say, show that. So I'll give you the 2 numbers. But the actual practicality of using this, that's why I said it's about importance about a 2. I'll show you how we use it in our next problem, okay? And it doesn't really come up very much. Okay, so let's show that -3 is a lower bound. I'll plug -3 in. 1, 0, -3, 2, and -5. I do my synthetic division. What can you tell me about your result? It switches sign. And because it switches sign, thus there are no solutions less than -3, meaning -3 is a lower bound for all of your solutions. So what we've basically done is I've shown you 2 pieces that would help you with the work that you did yesterday. So we're going to take 2 problems like you were working on yesterday and now apply these 2 theorems, the rule of signs and the upper and lower bound. And I would say this is most similar to the type of problems you're going to get on your test. So this is one you really want to focus through, and you'll be really good at these. Trust me. It says find all the rational zeros of the polynomial and irrational if there are any. When appropriate, use the rational roots theorem, upper and lower bounds, Descartes' rule of signs, quadratic formula, and all these other things. And if you're able to, sketch a graph. And so I'm going to first state this. The number of solutions total is how many? Is 3. Can I look at that and determine the total possible number of positive real solutions? I see 2. I see a sign change from the 1 to the -3 and the -13 to the 15. So 2 or 0. Now I'm going to apply what I showed you earlier on to save us some time. When I do p of negative x, if it has an odd exponent, does it change sign? Yes. If it has an even exponent, does it change sign? No. So we have a negative x to the third, a minus 3x squared, a plus 13x, and a plus 15. So again, that will help you move through that a little bit more quickly and help you from making mistakes. How many sign changes do you see there? 1. Now, if you were to subtract 2, you get negative 1. You can't do that. So you can have negative 1 solution. So we know we either have 2 positive real and 1 negative, or we have 0 positive real and 1 negative. Okay. If we had 0 positive real and 1 negative, then how many imaginary solutions would we have? 2. So I don't see that factoring, so let's list our choices. What are our p's? Yeah, so our choices are going to be positive or negative 1, 3, 5, and 15. Sweet. Let's try them. What do you want to try first? Let's try 1. Now, would it be reasonable to try negative 1 as well? Sure. And the reason why is as you look here, we have some alternating signs. And we also have, we don't have a situation where we have all positive. If I had all positive, then choosing negative 1 or choosing positive 1 would be bad, right? So are we using the upper and lower bound theorem? Yeah, we are. We're kind of saying, well, because I don't see all positives, I can plug in a positive number. So that's why I say that sometimes we use the upper and lower bound theorem without even really knowing it, okay? So, all right, we try 1. 1 minus 3 is negative 2, minus 13 is negative 15, plus 15 is 0. So if 1 works, what's the factor? Awesome. I'll let you catch up. We divided a cubic. We come up with a, what degree is this? A quadratic. Quadratic. Awesome, because we could solve that using quadratic formula or by factoring. So we know we're home free. This is x minus 1 times x squared minus 2x minus 15. Does x squared minus 2x minus 15 factor? Great. So my solutions are what? Negative 3, 1, and 5. Now, here's my favorite part. Negative 3, it was one of your choices. Positive 1, it's one of our choices. 5, it was one of our choices. How many negative real solutions do we have? 1. How many positive real solutions do we have? 2. For a total number of, it's like predicting the problem before we even do it. You know what I mean? That's pretty sweet that we were able to verify it ahead of time. Can we sketch this graph? Yeah. So I have solutions of negative 3, positive 1, and positive 5. Is this going to finish up or finish down? It's going to finish up. So I'm going to start down, and I have all single roots. And one thing I could do is it has a y-intercept of 15. So, you know, as I pass through the y-axis, I could just mark that as a 15 right there. So maybe this would be like, I don't know, 30. And, you know, part of you is saying, well, yeah, I mean, how accurate is that graph? I mean, come on, Mr. Gens. You know, well, since you're challenging me, x to the third, and then what? What do we have? And our window, I'm going to go to negative 5. I'm going to go to positive 7. Scale every 1. And a y value, I'm going to go up to, I'm going to go down to negative 40. And a max up to positive 40. and a tick mark every 15. And I don't know what you guys think, but remember, Descartes, Newton, they didn't have calculators. So how accurate were they with their graphs? Extremely accurate. I think that's pretty sweet. Last problem. Flip it over. Total number of solutions. There are 5. Number of positive real. How many sign changes do you see? I see 1 sign change here. I see 1 sign change there. I see 1 here. I see 1 there. So it looks like I have a total of 4 or 2 or 0. Less by a factor of 2. I am now going to list p of negative x. If it's an odd power, does it change sign? Yes. So I have negative x to the 5th minus 3x to the 4th plus x to the 3rd plus 11x squared plus 12x plus 4. How many sign changes? 1. So this guarantees there's for sure 1 negative real solution, which is kind of neat. I mean, we'll see if that pops up in our work. All right, so choices. And as you're complaining about the problem, you should be very thankful right now, because what have I made for our p's? Yeah, 1, 2, and 4. So, I mean, it's not like I've given us just a ton of choices. I've tried to narrow it a little bit because I care about you. And so, what would you like to try? I think 1's a great idea. 1 minus 3 is negative 2. Minus 1 is negative 3. Plus 11 is 8. Minus 12 is negative 4. Plus 4 is 0. Oh, all right. Smiley face. Got it. All right, we divide. Okay, did we come up with all positives? No, so 1 is not, an upper bound. So, there we could try 2 or 4. We could try. Let's just try 1 again. I mean, it worked once. It might work again, right? Could be a double root. So we plug in 1, we get 1 minus 2 is negative 1, minus 3 is negative 4, plus 8 is 4, minus 4 is 0. Oh. Let's divide it again. So you get x squared, or you get something you can factor. Can I factor it? It does factor. And so this is the point at which I stop and I say, I will not try the rational roots theorem again. Rather, I will factor it. I'm going to take out what? X squared. I get x minus 1. And I'm going to take out a negative 4. And I get x minus 1. Factor out now the x minus 1. And we get x squared minus 4. So I have x minus 1 times x minus 2 and x plus 2. And because I have the other two x minus 1s, it'll be x minus 1 cubed. So that's the factorization. So my solutions are plus or minus 2 and 1, 1, and 1. So let's see the awesomeness that lies before us. It is kind of, but you know, this is important theory moving forward, especially if anybody's considering a math major at all. I mean, this analytical part of our work is priceless. So look at this. I've got +1. I've got positive and -2. How many negative solutions do I have? 1. It's -2. How many positive do I have? Sweet. For a total of 5. Because 1, 1, and 1, that's 3, and then the 2 is number 4. I mean, right? Let's graph it and be done. So I know it has a y-intercept of what? 4. So I'm going to go to the right one, and that's a triple root. And then I go to 2, and I go back to -2. It's to the 5th degree, so it's going to end up. It's going to begin down. And I know I passed through 4 up there. So it's hard to predict the behavior entirely, but I'm going to guess it does something like that. I triple root there, just barely goes down and comes back up. And if you were to graph this, Jens, read it off to me. X to the 5th. Okay, and my window, I'm going to go up to x min. I'm going to go back to -5. X max, I'm going to go +5. Scale every 1. X min, I'm going to go to -8. I'm going to go to +8. I'm going to go tick mark every 1. And so it might jump off the screen here. And it does. So I wasn't able to show that. But look at that. Look at that behavior, how it just barely dips down. If I even change my window a little bit, it said -8 to +8. If I go -5 to +5, I think it's awesome that we're able to show that little, what we might call even hidden behavior existing right there. That's pretty sweet that we know that. It took us 4 minutes to, come up with and graph it. Very efficient in the days of Newton and whatever his name is, Descartes. Okay, here we go. So whenever I give this assignment, people do way too much work. I don't want this to be an assignment that involves a ton of work. So when you do 51 through 56, all you are doing is finding the number of positive real, the number of negative real, for a total of, in this case, 3 or 1 reals. You are not solving the entire polynomial and graphing it. Every year, people go back and do this assignment because they get behind. When they go back and do it, they try to solve all of them. And the funny thing is, many of these problems don't actually have any rational solutions. They're wondering why they can't figure them out. You never were supposed to. Just diagnose it. 57 through 60. Bounds. So remember when we plugged in the number and we used our synthetic division, we said, oh yeah, they're all positive, so therefore it would be an upper bound. And you plugged in another number. You came up with alternating signs. You said, oh yeah, now it's going to be a lower bound. That's all you do. Plug them in, synthetic division, say, yep, it's an upper bound. Plug it in, synthetic division, yep, it's a lower bound. It's 65 and 69 that I want you to do what we did in class for our last 2 problems, where you list the number of real solutions, positive and negative. You use the rational roots theorem. You find all the solutions. You sketch the graph. You do the whole process from beginning to end. That's what I want to see with those last 2. Does everybody understand that these first 2 sets right here are supposed to be quick and easy? In fact, it's very possible you could get these done before the hour is over. Well, wait a minute. We're going to 5. You could for sure get this set done, and then you would just have these and those. B. Rodham, what up? Got it. With that, you have bounds. So you're doing the upper and lower bounds there. Okay. Hope I see you guys tonight at the musical.